Okay, today we're going to be looking at continuing our trig work on double angle formulae. So it's linked to the lesson we did previously on sine of a sum, sine of a difference, cos of a sum, and so on like that. So let's have a look at what they are. You're not given these. The ones last time round, you're going to be given them in the formula book, but these ones you aren't. You're either going to have to learn them or learn how to derive them. And we derive them by where we had a and b in our formula before, let b equal to a, and sub it in. So instead of having sine a cos b plus cos a sine b, we have sine a cos a plus cos a sine a, so we end up with sine of 2a being 2 sine a cos a. Now, for cos 2a, we've got three different versions. We have the derived version. Cos of a sum was cos minus sine sine, so when they're both the same, we end up with cos squared a minus sine squared a. Now, that's the derived version. We tend not to use that one. We'll tend to use one of two other versions. And you'll find the other ones by doing the work from year 12, getting one of the formulas from year 12, the Pythagorean one, cos squared plus sine squared equals 1, and substituting. So where I've got cos squared minus sine squared, I could write it as cos squared a minus sine squared is 1 minus cos squared. And rewriting that, I've got cos squared plus another cos squared, so I've got 2 cos squared a and then minus 1. So that is a second version of cos 2a. And the third version is replacing the cos squared with a 1 minus sine squared. I've still got the minus sine squared from the derived version, so we end up with 1 minus 2 sine squared. So the idea is we tend to have equations to solve that involve cos 2a, and if it just involves sine, we'd use this version. If it just involved cos, we'd use that version. Tan 2a, there's only one version. Stick b equals to a, and we get tan plus tan becomes 2 tan a on the top, and 1 minus tan becomes 1 minus tan squared. And that's all there is to those ones there. So either learn them or learn how to derive them, because you're not given them. But let's have a look how we're applying them. So the examples we've got 4 rewriting ones. So if we've got an expression 2 cos squared 30, these are degrees by the way, 2 cos squared 30 minus 1, well that looks like this version of cos of the double angle, so it's going to be cos of 60. And since we've got a numerical value, we can work out what cos 60 is, the same as sine 30, it's half. 2 sine 45 cos 45 is sine of a double angle, so it's sine of double 45 sine 90, and sine 90 degrees equals 1. These ones are in terms of x, so leave them in terms of x. 1 minus 2 sine squared is this version of cos 2a here, so it's cos of the double angle, which is 10x, and 2 tan over 1 minus tan squared is tan 2a, where a equals 3x, so that becomes tan of double 3x, which is 6x. So that's just rewriting the expressions there. Now, let's have a look at, we might refer to this to see which version of cos 2x we're going to use. And as I said before, cos 2x plus 3 sin x equals 2, x lies between 0 and 360. I'm going to be using this version here. Because I've got sin x in, I want to use the version of cos which just has sine in. So I'm going to write it as 1 minus 2 sine squared x plus 3 sine x equals 2. And because I'm fairly lazy, I'm going to treat it as 1 minus 2y squared plus 3y equals 2. So I'm writing less basically, where y equals sine x, and rewrite to get 2y squared minus 3y plus 2 minus 1 plus 1 equals 0. Factorise it. Hopefully 2y minus 1 and y minus 1 equals nothing. Let's have a check. I get 2y squared minus 2 minus 1 is minus 3 plus 1, yeah. So y equals a half, or 1, and that equals sine x. So sine x equals a half, x equals 30 degrees, 150 degrees, 0 to 360, and sine x equals 1 is just going to be at the top 90 degrees. Okay, and I've got my 3 solutions there. Similarly to solve example 3, solve tan x times tan 2x equals 1. I'm going to let t equal tan x in this case, and get hopefully a quadratic and solve it and get my answers. X though is in radians in this case here. So tan x is t times tan 2x. 2t over 1 minus t squared equals 1. So 2t squared cross multiply equals 1 minus t squared. T squared equals, 3t squared equals 1. T squared equals a third. So t equals plus or minus 1 over root 3. And that's whatever tan x is. And so do the inverse tan of those, and we get x equals, it's in radians, don't forget, I almost did it in degrees then, 1 over root 3, pi over 6. Add pi to it, becomes 7 pi over 6, almost got it wrong, and minus 1 over 3 is minus pi over 6, but add pi to that becomes 5 pi over 6, and 11 pi over 6, and that's before answers there. Okay. A couple more examples to look at here. A proof one. It's just showing that this fraction 1 minus cos 2x over sin 2x is equivalent to tan x for all values of x. Now, because I've got that cos 2x in this case, the only thing I can do on the bottom is write it as 2 sin x cos x. Okay, so I'm looking at the left hand side here. But on the top, I want the version, because I want a simpler fraction than I've got there. I've got 2 terms on the top. I want to eventually go to 1 term. I want to write it in such a way that I'm looking at the version of cos where the 1 is going to cancel out. And if I write the 1 minus 2 sine squared on the top, the 1 minus 1 cancels out, I'm left with 2 sine squared over 2 sine x cos x. And hopefully the 2's cancel out there, the sine x cancel with one of the signs on the top, you get sine x over cos x, and that's what I want because that equals tan x, and that's the right hand side, so that's good to go. So notice I've got the choice there. If I'd have used the 2 cos squared minus 1, I would have ended up with 1 minus 2 cos squared plus 1, and then I've got more work to do basically. I haven't got from 2 terms on the top to 1 term like I have there. Last one on this board here, express cos 3x in terms of cos x. Well, I'm going to use the fact it's a combination of the work from last time round. I'm going to split up 3x as 2x plus x, and I can write it as cos 2x cos x minus sine 2x sine x, and then do some substitutions. I want it all in terms of cos, so I want to do the version of cos 2x. That's just got cos in. So 2 cos squared x minus 1 times the cos x minus, now there's only one thing I can do with sine 2x. I can write it as 2 sine, I'll leave a bit of a space there, you'll see why in a minute. 2 sine x cos x, and because I'm going to times by another sine x, that sine becomes sine squared. And I'm nearly there because I can times this out to get 2 cos cubed x minus cos x, and then minus 2, instead of sine squared, back to the Pythagorean, 1 minus cos squared times cos. And everything's in terms of cos, I've just got to times it all out and tidy it all up. So I've got 2 cos cubed x minus cos x. I've got minus 2 times cos x, so I've got a minus another 2 cos x there. And I've got minus 2 times minus cos squared times cos, so that's going to be plus 2 cos cubed, so plus another 2 cos cubed. So I've got 4 cos cubed x minus 3 cos x. And just so I know what I was after, that was cos 3x. Now, so rewriting a cos 3x, everything in terms of cos.
1.
Okay, and the last example then is one of these, a bit like the last lesson where they give us a value for, in this case, just sine A, and they tell us that A is acute, which is good, so I can sketch it, work out what cos A and tan A is. and they want me to find expressions for sine 2a, or values, sorry, for sine 2a, cos 2a and tan 2a, exact ones. So I'm not finding what the angle A is, so I need to show it step by step. So I would have assumed it was acute anyway, and sine is opposite over hypotenuse there, and with a bit of Pythagoras we know that the other side is 15, beautifully to scale. Look at that 8 and that 15, it's fantastic, and it gives me that cos A is 15 over 17, and tan A opposite over adjacent is 8 over 15. They're all acute, so they're all positive, there's no issues with that. So let's have a look at these then one by one. Sine 2a. I would get in the habit of quoting what we had at the start. 2 sine A cos A. Stick in what I know, so it's 2 times 8 over 17 times 15 over 17. And so work that out. I've got 30 times 8, 240. 17 times 17, testing my maths early this morning, 289 I think that is there. And that's that. Cos 2a. You can do any of the three versions because we know what sine is, we know what cos is, so I can do cos squared minus sine squared, I could do 2 cos squared minus 1, I could do 1 minus 2 sine squared. I'm actually going to do the 1 minus 2 sine squared because they give me what sine A is. I might have made a mistake in cos A, we all know I haven't, but I might have made a mistake in cos A, so it's always worth using what I've been given. So sine squared is 64 over 289. So put it all on a common denominator, 289 there, 289 minus 128, and that equals whatever it does, 161 over 289, and that's cos 2a. I'll do the last one over here, tan 2a, messy fraction. I've got the values there so I can still see them. Tan 2a is 2 tan 1 minus tan squared, so it's 2 times 8 over 15 over 1 minus 64 over 225. Now, because I've got fractions within fractions, how I deal with it, I want to get rid of these 15 and 225, so I'm going to basically times everything, top and bottom, every single term by the 225. So I end up with a fraction, but not with fractions within fractions. So in this case here, when I do that, I've got 2 times 8, now before, and I've got a 15 left over when the 15 cancels into the 225. And in this case, I've got 2 different terms. I'm left with 225 there when I times by minus 64. So I've got to work that out. So 2 times 15 is 30, times 8, 240, over 221, 161, top every fraction, which tan can be, so no issues with that. So tan 2a is 240 over 161. If you've got time at the end, you could always use your calculator to find what angle A was, double it, and do sine of that, cos of that, and tan of that, and hopefully you would get these exact answers anyway. But that's how we do those ones.